ではお時間になりましたので始めさせていただきます。ではDeep Dive into ScalaC の深みへダイブという題名でクリス・バーチョルさんに発表いただきます。ではクリスさんよろしくお願いします。
Hi, I'm Chris, and I'm going to talk to you about the compiler. So today we're going to talk about what the compiler does to get your lovely Scala code, foo.scala, into Java bytecode or class files, foo.class. So we'll look at the steps it takes along the way, the various compilation phases and things like that. Then we'll look at the Scala C code itself. We'll look at a bit of history, and we'll see how the code base is structured. We'll see how you can use the plugin API to extend the compiler in various ways. And we'll have a look at how you can hack on the compiler itself. First, about me. I work for The Guardian. I work on the back-end APIs that support the website and the mobile apps. I am the creator of the Scala cache library, and as part of writing that, I wrote my first Scala macro, and ever since then I've been quite interested in macros, and as an extension of that I became interested in the compiler and how it works. I used to work here in Tokyo for M3, and I used to be an organizer of ScalaMatsuri, which is why I have the coveted red happy from last year. So why should you care about the compiler? Why is it interesting or useful? For me, I think it's interesting because it's a large Scala code base with a lot of history. So I think it's interesting to study it, and it's a tool that we use every day, so we should know how it works, at least superficially. More practically, it's useful if you want to debug why your compile is slow. If you want to write macros, or if you want to read other people's macros, it's quite useful to understand some of these concepts. And if you want to contribute to Scala, either by fixing bugs or just by making good, useful bug reports, then it's good to have some domain knowledge about the compiler. Okay, so let's look at what the compiler is doing to get you from foo.scala to foo.class. Before we do that, we should just look at some terminology. When you talk about the Scala compiler, you often end up talking about these three types of things: trees, types, and symbols. So I'll just go through those. First, trees, or abstract syntax trees, ASTs. So this is a data structure that the compiler uses to represent your Scala source code. And you can play around with these trees and see what they look like quite easily using the reflection API in the REPL. So if I can use my pointer. So I just import the reflection API here in the REPL, and then I'm using quasi-quotes, this little Q thing with a string after it. This is called quasi-quotes, and this is a feature of the reflection API that will parse the string as Scala source code. So I'm giving it the string A plus B and saying, this is a piece of Scala source code, please parse it for me. So it does that, and it produces a tree, an abstract syntax tree. And the tree that it comes up with looks like this on the right. So I'll just quickly go through what this tree means. At the root we have an apply node, which means that this is a function application. It means you're calling a function. On the left-hand side of the tree we have the function that you are calling, and on the right-hand side we have the arguments that you're passing to the function. So you can see that we're calling the plus method on something called A, and we're passing it something called B. And here we don't know what A and B are, because this is just syntax. So A could be anything, and B could be anything, but this is this is the syntax of the thing that we're doing. So types. Scala is famous for its quite complicated type system. We have many different types of types. Like we have existential types and path-dependent types and phantom types and all kinds of types. But we won't go into that in too much detail in this talk. We'll just say, like, you probably know vaguely what type means. Symbols. So the symbol is kind of the name of an entity in your program, whether it's like a val or a class or a method. Anything that you can reference in your program has a name, a way of looking it up and accessing it. And all of this information is stored by the compiler in a data structure called the symbol table. Okay, so what is the compiler doing? This is going to be split over 2 slides, so I'll just go through it one step at a time. So starting at the left-hand side, over here we have your input, your foo.scala source code. And this input will go through a number of phases until eventually becoming bytecode at the end. So the first phase that it hits is this parser phase, which parses the source code as Scala source, as Scala code. And after that, the output of that phase is a tree like this, an abstract syntax tree. At this point, you don't have any type information. You just know that if you got this far, it's valid, syntactically valid Scala source code. The next phase is called namer. This is what discovers the entities in your program, all of the classes and methods and things like that. And it assigns them symbols and puts them into the symbol table. So now you have your untyped tree and your symbol table. The next phase, typer, this is where all the really complicated stuff happens. Things like type inference and implicit resolution and all of the really difficult stuff that the compiler has to do, most of it is in this type phase. But by the end of that, you have a nicely typed tree. So now every node of your tree has type information attached to it. After that, you have about 20 more phases, which I've combined all into one little cloud unicorn thing. But you're basically doing a lot of tree transformations. And those transformations are usually one of 2 things. It's either some kind of optimization, so it's taking normal but not very performant code and optimizing it into slightly more performant code, or it's a kind of transformation that takes your code from something that's like human readable almost, like Scala source code, and transforming it into something lower level that's easier to turn into bytecode, because the whole point of this compilation process is to get to bytecode as the end result. So you're gradually getting it closer and closer to Java bytecode. So at the end of all of those transformations, you still have the same basic data structures. You've got your typed tree and your symbol table. Now we come to what's known as the back end of the compilation. This is where we get from those data structures to JVM bytecode. You can see there are 2 paths here. I'll go through the top one first. So the next phase is called iCode, and this generates something that's called, well, it's called iCode, but it's an intermediate representation. So the reason for this is kind of historical. It's because the compiler used to support multiple platforms, not just the JVM. For example, it used to support .NET as an alternative platform. So the idea was that you could create this intermediate representation, and then all of the different platforms could generate their bytecode based on the same intermediate representation. But nowadays, that's not really true. There's just the JVM as the only supported platform. So this intermediate step is a bit pointless. So from Scala 2.12, the default will be to skip this and take this bottom part here, just go straight from the internal data structures to JVM bytecode. And this will be faster, the compilation will be faster, and it will also produce better bytecode. This is already available as a compiler option in Scala 2.11, and it will be the default in 2.12. So here are all the phases in the compiler. If you type what's shown at the top, scala c -x show phases, then you get this output. This is just a list of all of the phases in the order which they're going to run. You can see that a few that I mentioned here, like the parser and the namer and the typer, they're listed here. So what can we do with this information about phases? One thing that we can ask or try and gain some insight into is why my compilation is slow. So if you type scala c -verbose, then it prints out loads and loads of stuff. But if you just filter that with grep to this pattern, then you can see how long the compiler spent in each phase of compilation. So that might give you a clue as to why your particular project is compiling slowly. But unfortunately, the answer to the question which phase is the slowest, it's always typer. This phase here, this is where it's doing all the work. Like, as I mentioned, it's doing type inference, it's doing something called lubbing, which is quite expensive, implicit search, and there's not much you can do about it. About the only thing you can do is buy a faster computer or use fewer implicits. Yeah, or just wait, go and make a cup of tea. There's no need to rush. Okay, so let's have a look at an example of what one of these phases is actually doing. This is one of the simpler phases. It's called patmat, and it's a phase that deals with pattern matching. So I have some sample code here. I have a def is greeting, which takes a word, which is a string. It does a pattern match on it, and returns a boolean. So let's see what the Scala code looks like before this patmat phase runs. So I'm doing scala c -x print typer, because the typer phase is the one that runs just before patmat. And then you can see this kind of pseudo-Scala-ish representation of what the code looks like. This is not Scala, but it's kind of like Scala. So this is the tree, the syntax tree, after the typer phase and before the patmat phase. And you can see it's still doing pattern matching. It looks very similar to the initial code that I wrote. So now we'll look at what it looks like after the patmat phase. So now I'm doing scala c -x print patmat. And you can see that the code has changed quite a lot. It's done a lot of stuff. It's created a synthetic val and things like that. But basically, you now have an if-else instead of a pattern match. So the reason for this is because Java bytecode understands if-else, but it doesn't understand pattern matching. There's no bytecode operation for pattern matching. So you need to translate it into an if-else, which corresponds more closely with bytecode. Okay, so let's have a look at the Scala C code base itself. Firstly, a little bit of history. 2004, Scala 1.0 was released. At that point, the compiler was written in Java. Then, only 2 years later, Scala 2.0 came along. That was a complete rewrite of the compiler and the standard library as well, I think. At that point, it became known as NSC, which is the new Scala compiler. and it's still called that. If you look at the compiler now, it's still using NSE in its package names. Then for the next few years, nothing very exciting happened. I mean, they added a lot of new language features into Scala, so they obviously extended the compiler to deal with those, but nothing groundbreaking. 2011, there was an experiment to add .NET as an alternative backend, but for various reasons they decided not to go ahead with that, and they took it out, and so that's now gone from 2012. 2013, Scala.js came along, it kind of exploded onto the scene, and is still doing very well, it's very popular now. There were not actually any changes to the compiler for Scala.js. There's no specific support in the compiler for Scala.js. The way Scala.js works, it's all done with plugins, which we will look at later, and a few Scala macros as well. And then a little bit of future history. From 2.12, the new backend and optimizer that I showed you will be the default. So there will be no more iCode. You'll go straight from your trees to JVM bytecode. So the size of the code base, it's this number here. So the size of the source/compile directory is about 64,000 lines of Scala. It also depends on quite a lot of the reflection API, which is a separate folder. So in total, it's about 80,000 lines, I would say. So it's quite a serious chunk of Scala. This is a cake. So the Scala compiler is a kind of prototypical cake pattern. It was actually written before anybody had kind of discovered and named the cake pattern properly. So it's kind of cake-like, but it's not called the cake pattern. But basically, the compiler is split into a lot of components. Those components are modeled as traits, and they declare dependencies on other components using self-type annotations, which is the kind of things that you would see in your standard cake pattern structured code. The only problem is that there are a lot of these components in the compiler, and a lot of dependencies between them. So on the next slide, I've tried to model or demonstrate this in a diagram to show all of these different components and how they depend on each other. I'll put it up for a few seconds without comment, so you can just bask in its glory, and then I will explain. Okay, so this is, I think this is all of the traits that are mixed into the global class, which is the entry point to the compiler. So down here at the bottom we have global. This is like the meat of the compiler. This is where the cake is baked. And then that extends all of this stuff here. Just to explain the diagram, if we have a solid arrow from A to B, it means that A extends or mixes in B. So global extends or mixes in plugins. And if we have a dotted arrow from A to B, like this, it means that A has a self-type annotation. So A declares a dependency on B. So I won't go into detail, but you can see that global contains a lot of stuff. All of this stuff, any methods or vowels that are declared in any of these, they all end up in the global namespace. So this means that when you first encounter the code base, it can be very confusing. Whenever you find a method being called, you have no idea where it was defined. It could be in any of these. So you end up doing quite a lot of grepping when you first start. But you get used to it. And actually it gets worse, because you quite often see this pattern So here we have the global class, and then inside global there's a field called analyzer, and then using early initialization, global injects itself into the analyzer as a field. So then that means that, and then the analyzer promptly does import global._. So that means that the global namespace, which includes everything, is also included in the analyzer namespace. So it's a bit of a mess. But anyway, there are simple parts to the compiler. This is quite a reasonable, easy to understand part. This is the main kind of entry point to the compilation process. It's in global.run.compile. This method takes a list of file names, which are your source files that you want to compile, and it actually compiles them. So this is a good place to start if you want to understand how the compiler works. So what is it doing? Step one, it's calculating what phases it should run and the order that they need to run, because each phase can declare dependencies on other phases. So they can say, I want to run before this phase and after this phase. So it calculates what order they should run in, and then it just loops through them. So for each phase, it loops through each input file, each source file. For each file, it runs the phase. At the end of each phase, it prints out any debug stuff that you told it to. And then it sanity checks various data structures after each phase, so that you can just check that the previous phase hasn't completely broken your data structures due to some bug. And then at the very end, it prints out any compile errors or warnings that it found. So I keep saying phase, but what is a phase in Scala source code? This is what it looks like. So there's this abstract class global phase, which you can extend if you want to implement a phase of your own. And the most important method that you need to implement is this apply method here, which takes a compilation unit as input, and it returns nothing, unit type. So a compilation unit is basically one file of Scala source code. For each source file, there is one compilation unit, and that includes the syntax tree for that file and various other data structures. And the important thing is that it's returning unit type, which means the only thing it can do is perform side effects. It's doing mutable transformations on everything inside this compilation unit. Which is quite not very nice for a lot of Scala developers who are used to doing things immutably. It's quite a shock to see this happening, but I guess for performance reasons it had to be done. So your phase will probably end up doing tree transformations. That's what most of them do. So there's a lot of utility code, utility classes around the compiler to help you do that. And one that's quite useful is this transformer trait, I think, or possibly abstract class here, which you can extend if you want to do tree transformation. So I have an example here. This is a transformer that takes all Boolean trues and turns them into false, all falses turns them into trues. And you can see that you do your tree transformation using pattern matching. So it will traverse the whole tree, and every time it finds a bit of tree that looks like one of these patterns that you define, it will do whatever's on the right-hand side. It will replace that bit of the tree. So it'll match here, find this bit of tree, it'll replace it with this bit of tree. And then if it doesn't match any of the previous cases, you just fall through to this case. Okay, so that's some of the code that's in the compiler. But now we're going to look at the plugin API that you can use to extend the compiler. Plugins are used in the real world in quite a few places. For example, if you've ever used scoverage, it's a test coverage tool that uses a plugin to instrument your code. Scala.js, as I mentioned, uses plugins to, so while you're compiling your code into bytecode, it's also compiling it into an intermediate representation which it can convert into JavaScript later. So I think it's called transpiling. It kind of piggybacks onto the Scala compiler to produce JavaScript as well as bytecode. Macro Paradise, which contains things like macro annotations, that's done using plugins, or a plugin. And also SBT's incremental compilation is technically not a plugin, but it's very similar to a plugin. So it's kind of instrumenting or gathering information about what dependencies you have between classes in your code so that it knows what it should compile. Plugin in Scala looks like this. It looks a little bit complicated because we have some nesting going on here, but it's reasonably simple. We have a plugin, my plugin, which defines one or more components like this. And then each component defines one phase like this. So the point of plugins is to add new phases into the compiler. You can add one or more phases of compilation. And you can define dependencies on other phases. So you can say, I want my phase to run after the typer phase. So you can say, at what point in the compilation should this happen? So for example, if you need type information, if you need a typed tree for your plugin for whatever reason, then you should run after the typer phase. So I'm going to show you an example of a plugin. And I quite like this idea that Scala.js has of using a plugin to transpile from Scala into another language. But I thought, what language do we all like even more than JavaScript? Basic. So I've written a little plugin that will convert your Scala into Basic. I'll just give you a little demo now. Okay, so I have some just normal Scala code here. It's got a def. It's got a def here. I've given it a special name so that my plugin can find it and it knows to turn it into basic. It's got some quite strange Scala code. It says while true, println. That's not something you do normally, but never mind. So before I compile, I'm going to run the compiler with my plugin. So I'm adding the plugin, which I already have in a jar here. And I'm going to do -x show phases. Oops. So here you can see it's added a new phase. Phase 5, just after the typer, it's going to run this basic phase, which generates basic code. Okay, so let's compile this code. So the plugin ran, it found my specially named method, and it converted it to a basic program. So it's written this new file, print hello forever.baz. Which looks like this. So now we can run this with our favorite basic interpreter. There you go. Okay, so not the most useful plugin in the world, but if you're interested, then the code is available online. So that was plugins, but maybe you don't want to just write a plugin, you want to actually extend the compiler itself, hack on the real compiler for whatever reason. Maybe you want to fix a bug. So you need to be able to build it on your local machine. And this is how you do that. We don't have that much time, so I won't go into detail on this slide, but basically here is how to get Ant to build Scala on your local machine. And then down here is how to reference that locally built version of Scala in SBT so that you can play around in the REPL. So my example of hacking on the compiler, did anybody happen to follow the SLIP 28 debate? It was last year, I think it was about November. Somebody quite reasonably suggested adding a JSON AST into the standard library, and the whole Scala community just exploded in a fireball of rage. It was quite fun to watch. So I don't really have any strong views about whether there's an AST in the standard library, but I do enjoy watching people get very angry about these things. And I thought, how can I make them angrier? So, why bother with why stop at adding a JSON AST to the standard library? Why don't we bake JSON into the language itself? So imagine if you had this new JSON keyword here, and then you could just write JSON, plain old JSON, inside your Scala code. How cool would that be? So that's what I did. So step one, I added the JSON AST to the standard library. So I added a new package, scala.json, and an AST. Just this is probably enough to get me death threats. Step two, I added a JSON keyword here. So if you've ever used the word JSON in your Scala code ever, I just broke that, so sorry. I also added a new token into the parser. And not shown here, I added a line that said, if you see the JSON keyword, then output the JSON token. Step three, I wrote a JSON parser, a really bad JSON parser, but it works. And interestingly, JSON tokens and Scala tokens are quite similar. For example, like a number, a decimal number, 1.23, is the same in Scala as it is in JSON, so you can parse them using the same tokens. So I managed to reuse quite a lot of the existing Scala parser and kind of piggyback on top of that. And then step four, I wired it all together. So this is inside the existing Scala parser in the compiler. I create my new JSON parser, and then I added a new case into this method here called expression 0 that says if you see a JSON JSON token, then you should start parsing as JSON until I tell you not to. So that was it. And now I can give you a little demo of that. So I'm running SBT console here, so I've got a REPL ready. You can see it's using my customized version of Scala 2.11.7, which I built earlier. So now if I type val foo equals JSON, and then I just type some JSON here, then it will parse it and turn it into Scala for me. So there you go, JSON literals in Scala. And the code for all of that is also online if you want to take a look. So we're nearly done, just a bit of further reading. I'll put the slides online so you can read these at your leisure. I recommend the one at the bottom. This was a really interesting talk about Dotty, the new compiler for Scala. It's being developed at the moment. This was at Scala World last year. Final remarks. So the Scala compiler is a marvel of engineering. So we should all be thankful for it. And I think we should all stop complaining about our compilation being slow. We should just be thankful that it works at all. So, thank you very much. We have about 5 minutes if you want to ask any questions.
質問がある方はどうぞ。そうですね。こちらのマイクまでいいですか。
Hi, I was just wondering, how many hit squads do you have after you because of the JSON thing?
None so far. I think everyone's happy to admit that it's a joke.
Well, none that you know of.
Yeah, there may be some ninjas on the way now.
Thank you very much for the talk. So you mentioned that the compiler itself is internally stateful and mutable, but you mentioned that there was a significant or a perceptible amount of kind of grief about that. Is there a move towards a more functional compiler, or is that just deemed completely unacceptable due to performance?
No, I think Dotty, the new compiler, will be a lot more immutable. It's structured in quite a different way. They have this thing called micro phases or mini phases, I think, which will allow much more of a functional style and just a much saner code base in general.
Maybe
you can speak up. Will performance will suffer if you have this cleaner code structure and smaller phases in the new compiler?
So the question was, will the performance suffer in the new compiler in Dotty because of immutability? I don't know is the answer, but I would guess that with some clever data structures, with persistent data structures and sharing and copy on write and so on, I don't think that performance does suffer that much. I think a lot of people who say that you should use mutability for performance reasons are kind of guilty of premature optimization or maybe unfounded optimization. You just have to measure. There's no other way around it. You've got to measure it and see. Okay, no more questions, so thank you very much.